Dear all, I would like to welcome you all in the lecture series of Basic Electrical Engineering. In this session I am going to discuss most important equations related to Module 3, Module 4 and Module 5. I have already discussed the important equations from Module 1 and Module 2 in the previous session. Kindly go through that. Module 3 comprises of transformers and a DC machine, and we will find out what are the important equations which you need to remember for the exam point of view. So first point, transformation ratio, secondary voltage by primary voltage, secondary number of turns divided by primary number of turns, first primary current divided by secondary current, that is called a transformation ratio, that is equal to K. So if K greater than 1, then it is known as step up transformer. If the K is less than 1, then it is known as step down transformer. Please note down this point. Another important concept is EMF equation of transformer. So we can able to write EMF equation for the secondary side, that is E2 is equal to 4.44 F into phi m into N2, where primary side EMF equation can be written as E1 is equal to 4.44 F into phi m into N1, where phi m is the maximum flux and F is the supply frequency. Here N is the turns. It is applicable. If it is primary side, we call it as N1. If it is secondary, then we can call it as N2. If we want, you can do one thing. Phi m can be modified. Some kind of numerical example. They may give in terms of flux density and area of the core. At that time, what you can recall, please remember the formula. So flux density is the ratio of the flux per unit area, phi m by area. Okay, therefore you can able to write one thing, phi m is equal to A into Bm after doing the cross multiplication. Same thing can be substituted over there. Are you getting my point? Is equal to 4.44 F into, instead of phi m, I would like to write A into Bm. Then turns will be as it is. And you can note down this point as well. Another important point related to transformer losses. There are two type of losses. One is copper loss, another one is core loss. The core loss can be divided as hysteresis loss and eddy current loss. Okay, so hysteresis loss can be computed using the formula. The hysteresis loss is directly proportional to Bm to the power 1.6 into F, where eddy current loss is directly proportional to Bm square, F square, T square, where T is the thickness. Okay, thickness of the material, thickness of the core. Okay, you can able to move on this equation. And also one thing, how to calculate the iron loss. Iron loss is nothing but the sum of hysteresis loss and eddy current loss. Okay, so this is regarding the core loss or iron loss. When it comes to copper loss, the copper loss can be computed by using this equation, I1 square into R1 plus I2 square into R2. This is concerning for primary side, where the second part is concerning for secondary side. I think you are understanding my points. Therefore, we can able to write the total loss, that is the sum of iron loss and the core loss, iron loss and copper loss. Wa means iron loss, WCU means copper loss. Iron loss is also known as core loss. Okay. Now let me move on to how to calculate the efficiency of transformer. V2I2 cos phi 2 whole divided by V2I2 cos phi 2 plus Wi plus WCU. What does it mean? This is your output, right? Okay, output. I'll be writing like this. OP means output. So this is also your output, right? Output. What is this? Can you imagine that? Can you guess? Can you make a guess? No need to guess. Already studied, right? This is your losses. Okay. So that means efficiency is the ratio of output divided by output plus losses. What is output losses? Output plus losses. Output plus losses means the input, right? Any confusion? If you are having any confusion, you can put up in the comment box. See. Eta means efficiency. Efficiency means output divided by output plus losses. What is output plus losses? Output plus losses means input. This formula you please remember. So then no need to by heart, you can remember. Wi plus WCU means losses, right? So this is a formula. Please do remember this. And a numerical example you can expect it. Suppose there are different type of loading. Suppose if the load is 25%, load may be 50%, load may be 75%. At that time, how to calculate the efficiency? Efficiency corresponding to the fraction of load can be computed by using the equation eta efficiency in terms of x. You can put x, eta subscript x, that is equal to x Vi cos phi into 10 to the power 3 divided by x into Vi cos phi into 10 to the power 3 plus Wi plus x square into WCU. What is x here? X is the fraction of load, or you can call it as a load factor or fraction of load. It may be in for 15% or 20% or 90%. If it is 90%, please take exit as 0.9. If the fraction of load is 75%, please to take x is equal to 0.75. Okay, so this formula is very important. You may ask me that why you are multiplying with the 10 to the power 3. Very simple. KVA will be converted into VA. That's all. That's why I'll be multiplying with 10 to the power 3. Why I am multiplying with 100? Why? Because it is better to express in terms of percentage, no? So that's why I would like to multiply with 100. I hope you are understanding my point. If you are hesitant to write like 10 to the power 3, do one thing. X into kVA cos phi divided by x into kVA cos phi plus Wi plus x square into WCU. The fraction of load that will be depending on the copper loss also. That is why it is multiplied with the x square. Okay. Now another important concept I want to tell you. What is the condition of maximum efficiency? Yes, the condition of maximum efficiency is such that the copper loss will be entirely equal to core loss. Then we will be getting the maximum efficiency in the transformer. What can be written as copper loss? I1 square into R01 is the form of copper loss. Wi means iron loss. Is it okay or not? Yeah. Now output kVA corresponding to maximum efficiency. So for the gate examination and all, you can expect similar kind of question. So the output kVA corresponding to maximum efficiency can be computed using the formula full load kVA into square root of iron loss divided by copper loss. This iron loss is also known as core loss, correct? Where x is known as square root of iron loss divided by copper loss, or you can write x is nothing but square root of Wi divided by WCU. Okay, so in spite of this, I can able to write x also, not a worry, not an issue. Okay, yeah, this formula also you can remember. So another thing is one of the concept related DC machine. Okay, DC machines also we are discussing in this chapter. In case of DC machine, remember that there are two type of armature winding. One is lap winding, another is wave winding. In case of lap winding, number of conductor per parallel path is equal to number of poles. Where in case of wave winding, the number of conductor per parallel path is fixed. That is 2. Very important. Another thing is important EMF equation of a DC generator. You can able to write EMF equation use two formulas. First one is Eg is equal to phi Zn by 60 into P by A, where phi is the flux, Z is the number of conductors, N is the speed of armature, and P is the number of poles, A is the number of conductors per parallel path. It is expressed in terms of volt only. Similarly, Eg, if you know the terminal voltage and the armature resistance and armature current, then you can use the formula Eg is equal to V plus IAR. This much of volts only. Do remember this. Then DC machine will act as motor and generator. Then when it comes to motor, you can able to write total when a current carrying conductor is placed in a magnetic field, it experiences a force. That is a working principle of DC motor. Therefore, force can be computed using the formula V into I into L Newton. Okay, where V is the flux density, and I is the current, and L is the length of the conductor, and I is the current through the conductor. So when it comes to DC motor, always remember that back EMF can be written as V minus I. Here terminal voltage is greater than back EMF. Okay, and also you can use the similar kind of formula which is used in DC generator. EB is equal to phi Zn by 60 into P by A. Here you have to notice, here EB is equal to V minus IARI. But EG, what is EG? EG means generated EMF. EG is nothing but V plus IARI. Do remember this point very seriously. Okay, IA into RI. I think you are understanding whatever I am explaining. Then armature torque you can able to calculate using the formula 0.1595 IA PZ by A Newton meter. So this you can remember. Any manner you can write it. This is very important for problematic questions. When it comes to problem, you have to solve this. Where parameters I already explained, phi, Z, I, all those things I think you know. In case of module 4, you have to remember what is synchronous speed. Synchronous speed can be computed by using the formula 120 F by P, where F is the frequency, supply frequency, and P is the number of poles. So EMF equation of alternator or AC generator can be computed using the formula E is equal to 4.44 F into T phase into Kp into Kd, where Kp is the related to the turns. So turns and number of conductors are correlated each other. In case of induction motor, second part is induction motor. The resultant flux is the 1.5 times of the overall flux or the total magnitude of flux. So slip speed you can able to calculate by using the formula Ns minus N, where Ns is known as speed. And slip wave you can able to calculate using the formula ns minus n divided by ns. Finally, the rotor frequency you can able to calculate using the formula f